Imagine you're handed the most thrilling murder mystery novel ever written.
Okay, I like a good mystery.
Right, but there's a catch. You're only allowed to read it one single word at a time through a tiny peephole.
Oh, that sounds awful.
Yeah, so you see the word the, and then it disappears, then detective, and it disappears. By the time you finally reach page 200 to find out who the killer actually is, your brain has completely lost track of the clues from page 1.
I mean, you'd vaguely remember there was a murder, but all the nuance, the suspects, the timeline, it's all just gone.
Exactly. It sounds like an incredibly frustrating way to read a book. You'd never be able to hold the whole story in your head.
No, definitely not.
But for decades, that is exactly the frustrating, bottlenecked way we forced artificial intelligence to try and understand human language.
Yeah, it really was.
And if you're listening to this right now, you probably remember the exact era we're talking about. A few years ago, chatbots were basically these confused, goldfish-brained robots.
Yeah, the memory was practically non-existent.
Right. You'd ask them a two-part question, and by the second part, they had completely forgotten what you initially asked. But then, seemingly overnight, everything changed. We suddenly had these highly articulate assistants that could track long, complex philosophical debates with us.
It was a massive paradigm shift. I mean, people often think there was some gradual, slow evolution behind the scenes, but, well, the reality is that the leap forward was triggered by very specific, fundamental changes.
Changes to the actual architecture of how these machines process information.
Exactly.
And that is exactly what we're getting into on today's deep dive. We are looking at the foundational blueprints that completely revolutionized how computers read.
Two massive breakthroughs from researchers at Google.
Yeah, specifically the 2017 paper Attention is All You Need and the 2018 paper on BERT. The mission today is to decode the incredibly dense, math-heavy science behind these models and translate it into plain English.
No computer science degree required.
Exactly. We want to look at the exact problems early AI faced, the well-intentioned but flawed ways engineers tried to solve them, and the brilliant novel ideas that make your current smart devices actually smart.
So, to really appreciate the leap, we first have to look at the trap early language models were stuck in.
The peephole trap.
Right. Before these breakthroughs, the dominant systems for processing text were called recurrent neural networks, or RNNs, and they operated on a strictly sequential basis.
Sequential meaning like one thing after another.
Exactly. When an RNN looked at a sentence, it didn't look at the sentence as a whole thought. It read the first word, did some math to calculate its internal understanding, its state basically, and then moved to the second word.
Okay, step by step.
Right, you would then update its understanding based on that second word, then move to the third, and so on, step by excruciating step.
I always picture this like a factory worker standing at a conveyor belt. You can only look at the one item directly in front of you on the belt. You inspect word 1, it rolls away. Word 2 rolls up, you inspect it, it rolls away.
That's a great visualization. The computer's understanding is inherently tied to the passage of time. Step 3 just cannot happen until step 2 is entirely finished.
But wait, I have to push back here. You say that like it's a bad thing. But isn't reading word by word from left to right exactly how humans read?
Well, sure.
Like, I don't absorb an entire novel in a single glance. I read sequentially. Why was this considered such a naive or problematic solution for a computer?
It's a fair point, because it does mimic human reading on the surface. But researchers realized this conveyor belt model created two massive crippling flaws for a machine.
Okay, what's the first one?
The first is the memory issue, often called the problem of long-term dependencies. Because the computer is processing everything sequentially, constantly overwriting its current state with the new word, the path the data has to travel is just too long.
So it's forgetting as it goes.
Precisely. By the time it gets to the end of a dense paragraph, the mathematical signal from the first sentence has essentially degraded to zero. It's faded away.
Okay, so if I'm telling you a long story about my cousin Jimmy, and I describe his car, his job, his dog, and then 20 minutes later I just say he.
Your human brain instantly connects he back to Jimmy.
Right. But the computer's conveyor belt pushed Jimmy off the edge into the incinerator 20 minutes ago. It has no idea who he is.
Exactly. The system loses the thread of context over long distances. And the second major flaw of the conveyor belt is speed. Or rather, the total inability to scale up speed.
Because it's waiting on the previous step.
Yes, exactly. Modern computer chips, especially GPUs, graphics processing units, are powerful because they are designed to do thousands of calculations simultaneously, in parallel.
Okay, so they like doing things all at once.
Right. Think of a GPU like a factory with 10,000 workers ready to assemble parts. But because the RNN is sequential, you can't use them. You're handing the entire sentence to just one worker, while the other 9,999 workers just stand around doing nothing.
Just waiting for their turn.
Right. You can't hand a whole book to a supercomputer and say, read this all at once. You are bottlenecking billions of dollars of hardware into a single file line.
So you have a supercomputer, but you're forcing it to read word by word like a struggling first grader? That sounds incredibly inefficient.
It was a massive roadblock.
Yeah.
Training these models took weeks or months, and the results were still poor because of the memory loss. That is what set the stage for the first massive breakthrough in 2017.
The famous Google paper.
Yes. They introduced an entirely new architecture called the transformer.
And the big claim to fame here is that the transformer completely ripped out the conveyor belt. No more sequential steps, no more one word at a time.
Exactly. They introduced a mechanism called self-attention.
Self-attention.
Yeah, this was radical. The transformer allows the model to ingest the entire sequence of words simultaneously. It draws direct connections, they call them global dependencies, between the input and the output without caring at all about how far apart the words are physically on the page.
I try to visualize this like a classic detective's murder board. You know, the giant cork boards you see in movies with all the photos and red strings connecting everything?
I like that.
Yeah. Instead of reading a detective novel on a conveyor belt, the AI acts like a detective standing in front of a giant cork board. Every single word from the paragraph is pinned up on that board at the exact same time.
Right. All visible at once.
And the AI just stands back, looks at the whole board, and draws red strings between the words that are related to each other, no matter if one word is on the top left and the other is way down on the bottom right.
That captures the essence of it perfectly. Self-attention is a mechanism that calculates how much attention every single word in a sentence should pay to every other word in that same sentence. It instantly connects all positions.
But mechanically, how does a computer actually do that? The source material gets really deep into the math here, throwing around terms like query, key, and value.
Yeah, it gets a bit dense.
I'm going to be honest, when I read that, it sounded like database management jargon. I completely lost the thread. How do those concepts help an AI draw red strings on a corkboard?
Let's step away from the heavy math and look at the logic. In this system, every single word is represented by a list of numbers, and the network generates 3 distinct lists for every word: a query, a key, and a value.
Okay, I'm still struggling. Can we ground this in a physical space? Like imagine we are in a massive cavernous library or a filing room.
We can definitely work with that. Let's say you walk into this massive filing room because you are looking for a very specific piece of information. The concept you are searching for, your search term, is your query.
Right, and this room is full of thousands of filing cabinets. Every single cabinet has a label on the outside of the drawer describing what is inside. So those labels on the outside, those are the keys.
Yes, exactly. So the mathematical mechanism takes your query, what you're looking for, and it compares it against every single key, the labels on the cabinets, all at once.
Oh, wow. All of them.
Right. It's essentially assigning a percentage score to how well your search term matches every single label in the room.
Got it. So if I'm trying to figure out what the pronoun it refers to, it is my query. The system scans all the key labels in the sentence, finds the cabinet labeled the green apple, and says, aha, high match percentage.
Exactly.
Oh.
And once it finds the cabinets with the highest matching scores, it opens those drawers and pulls out the actual documents inside. Those documents, the core information it extracts to build its understanding, are the values.
Okay, that clicks.
Yeah, it mixes those values together based on the match scores to figure out exactly what the word means in that specific context.
Okay, that makes so much more sense than just staring at the formulas. The AI is basically constantly asking, what am I looking for, what's available, and what's the actual content I need to pull?
Precisely.
But here is the craziest part of the whole transformer architecture to me. It doesn't just do this library search once. It uses something called multi-head attention.
Right. The researchers found that relying on just one single attention mechanism, one set of queries, keys, and values, sometimes averaged out the nuance of a sentence. So instead of one pass, they ran multiple attention mechanisms in parallel.
So they ran a bunch at once.
Yeah, in their base model, they used 8 parallel heads.
So going back to our murder board analogy, it isn't just one detective looking at the corkboard. It's like having 8 totally different experts sitting in chairs, staring at the exact same board simultaneously, but they are all looking for completely different clues.
That's a highly accurate way to frame it. The source material refers to this as allowing the model to attend to different representation subspaces.
Which means what practically?
It means, while Detective 1 is drawing red strings between words based purely on grammar and sentence structure, Detective 2 is drawing strings based on the emotional tone of the words.
Oh, I see.
Yeah, and Detective 3 might be looking strictly at who is performing the action versus who is receiving the action. By having 8 distinct heads working at the same time, the model captures a profoundly deep, layered understanding of the relationships between the words.
And because they ditched the conveyor belt, all 8 of these detectives can do their work instantly, right? They don't have to wait for the words to roll by.
Exactly. Because it looks at everything simultaneously, they could unleash the full power of modern GPUs. The researchers were able to train this massive model in just 12 hours.
12 hours. That's insane.
It really is. Prior to this, training a less capable model would take days, sometimes weeks, of constant computing.
All right, so let's take a breath and figure out where this leaves us. The transformer breakthrough gave AI a massive speed boost because it could parallelize the work.
Right.
And it completely solved the memory issue because the corkboard lets it see the beginning of the book and the end of the book at the exact same time. It doesn't forget.
Correct. The architecture was revolutionary.
But having a fast memory isn't the same thing as actual comprehension. I mean, I could stand in front of a murder ward full of documents written in a language I don't speak. I can see all the words instantly. I haven't forgotten any of them, but I still have no idea what the story's about.
That's a great point.
How did we get the AI to actually understand the context of human language?
That is the exact logical gap that brings us to the next massive hurdle the industry faced. Because you are absolutely right. Having the physical architecture of the transformer was only half the battle. The other half was figuring out how to actually train that architecture.
Right.
And prior to 2018, the training methods being used were still fundamentally flawed. They were treating language like a one-way street.
What do you mean by a one-way street? If they have the corkboard, why couldn't they understand it?
Well, let's look at the models that existed right before our next breakthrough. You had models like early OpenAI GPT and a model called Elmo. Early GPT was trained strictly left to right. It tried to understand the meaning of a word based only on the words that came before it in the sentence.
That feels like trying to guess the twist ending of a complex mystery movie, but the theater kicks you out halfway through.
Yeah, exactly.
You have no idea what clues are coming in the third act that would completely change the meaning of the early scenes. You need the end of the sentence to understand the beginning sometimes.
Exactly. Now, Elmo tried to be a bit smarter. The researchers trained one model to read strictly left to right. Then they trained a completely separate model to read strictly right to left.
Okay, so both directions?
Yeah, but then they took the outputs of both models and just shallowly mashed them together at the end.
Wait, why is mashing them together considered shallow? If you have one reading left to right and one reading right to left, haven't you covered the whole sentence?
It sounds like you have, but you haven't built true deep context because the two models never actually interact during the learning process. It's like having two students read half a book each. Student A reads the first half, student B reads the second half, and they just staple their book reports together at the end without ever talking to each other.
Oh man, yeah, that's not going to be a good report.
Right. The final report will have all the events, but it will miss all the overarching themes and subtle connections that span the whole book. True understanding requires looking at both directions simultaneously while you are learning.
Okay, but this is driving me crazy. If the transformer architecture we just talked about gave them the mechanical ability to look at all the words at once in any direction, why were these researchers deliberately restricting their models to read in only one direction? Why hobble the machine?
It wasn't because they wanted to, it was because they felt they had to. Standard language models are trained through prediction. You show the AI a sequence of words and ask it, what is the next word? If it guesses wrong, it adjusts its internal math. If it guesses right, the math gets stronger.
Okay, prediction. Makes sense.
But think about the math of the transformer's self-attention. It looks at everything at once. If you let a standard model see the whole sentence in both directions while trying to guess a missing next word, the math would simply loop around, look ahead at the actual answer, and feed it back to itself.
Wait, so it would indirectly see itself?
Yes.
Ah, it would literally just cheat on the test.
Exactly. It wouldn't learn anything about context or meaning. It would just use the multi-directional red strings to find the answer key and copy it. So researchers put blinders on the AI, forcing it to only look left to right. specifically to prevent it from cheating during training.
Wow. So they deliberately crippled its ability to understand context just so the training mechanism would work. That brings us to the second massive leap of BERT.
Yes, the 2018 Google project that completely changed the game.
BERT stands for bidirectional encoder representations from transformers. And the engineers realized that being unidirectional was severely limiting the AI, especially for tasks where you needed the whole context. So they had to invent a novel solution to the cheating problem.
They did. And their solution was surprisingly playful. They introduced something called the Masked Language Model, or MLM.
Masked language model.
Right. Instead of asking the AI to predict the next word at the end of a sentence, BERT takes a whole sequence of text, randomly blanks out 15% of the words right in the middle, and asks the AI to guess what those blanked out words are.
I love this concept so much because it is literally just a giant game of Mad Libs. Or fill in the blank.
Exactly like that.
If you have a sentence like, the man went to the blank to buy a gallon of milk, the AI doesn't need to read it left to right to guess the next word. It looks at the left side, man went, and it looks at the right side, buy milk. The entire surrounding context heavily points to the blank being a word like store.
It's an elegant solution. Because the word is completely erased and replaced with a blank token, the AI can look at the entire sentence simultaneously, bidirectionally, without being able to cheat, because the answer literally isn't there anymore.
That's so smart.
It really is. It forces the AI to build a rich understanding of how words interact from all sides.
And this is exactly why today, when you type a half-finished sentence into an email or a text message, the computer instantly suggests the exact right word to end your thought. It is playing Bert's game of fill in the blank with your typing.
Fundamentally, yes. That predictive power comes from this type of training. But the authors of BERT realized there was a subtle flaw with this Mad Libs approach. If the AI spends all its time learning to predict words that are replaced by a literal mask symbol, it's going to get confused when it gets deployed into the real world.
Because in the real world, when I ask a chatbot a question, I don't put giant mask symbols in my text. I just speak normally.
Right. The AI would become over-reliant on the presence of that explicit blank space. So the researchers threw a fascinating 10% curveball into the training game.
A curveball.
Yeah, of that 15% of words chosen to be guessed, BERT doesn't always put a blank space.
Yeah.
80% of the time, yes, it uses a literal mask token.
Yep.
But 10% of the time, it just leaves the actual correct word sitting right there. And the final 10% of the time, it replaces the target word with a completely random, incorrect word.
Wait, let me make sure I'm hearing this right. Instead of a blank, it throws in a wrong word. So a sentence like, my dog is very hairy, might randomly become, my dog is very apple.
Yes. They deliberately fed it garbage data 10% of the time.
I have to push back on this. If I'm trying to teach a toddler what a dog is, I don't point to a golden retriever and say apple. That's just going to confuse the kid. Why would you deliberately sabotage the AI's training data by lying to it? Doesn't that ruin the learning process?
It sounds counterintuitive, but it's actually the secret sauce of BERT's deep comprehension. By occasionally leaving the correct word or swapping in a wrong word, you force the model to build an incredible amount of internal skepticism.
Internal skepticism.
Yeah, the model learns that it can never trust any single token fully. It never knows which word it's going to be asked to predict or which word might be an imposter designed to trick it. So it is forced to constantly maintain a rich contextual understanding of every single word in the sentence at all times. It has to double-check everything against the surrounding context. It reads, my dog is very apple. And instead of just accepting it, the deep context of the words dog and very forces the AI to essentially say, hold on, apple makes no grammatical or logical sense here.
This must be one of the trick words.
Exactly. It realizes the underlying meaning should be an adjective describing an animal's coat, like hairy.
That is absolutely brilliant. It's building a bulletproof web of meaning. It's not just passively reading. It's actively interrogating the sentence to make sure the words actually belong together.
It creates a highly resilient language model. And BERT didn't stop at just understanding single words. They introduced a second pre-training trick called net sentence prediction, or NSP.
Because predicting individual words is one thing, but to be truly useful, an AI needs to know how entire complex thoughts flow together.
Exactly, right? If you want an AI to summarize a legal document or answer a nuanced question, it needs to understand how paragraph 1 connects to paragraph 2. So to teach it this flow, they fed BERT pairs of sentences. 50% of the time, the second sentence actually followed the first in the original text. The other 50% of the time, it was just a random sentence pulled from somewhere completely different.
And what was the test?
The model simply had to answer one binary question. Is this the actual next sentence?
So it looks at the man went to the store, he bought a gallon of milk. Is that the next sentence? Yes, logically it follows. Then it looks at the man went to the store, penguins are flightless birds. Next sentence, no. There's no logical connection.
Exactly.
You are literally teaching the machine logic, cause and effect, and narrative flow without ever having to sit down and manually code complex grammar rules.
And the real-world impact of this training was immediate and undeniable. By taking this pre-trained BERT model, a model that had already played billions of rounds of fill-in-the-blank and next sentence guessing researchers could take it, add just one simple extra layer of code on top to fine-tune it for specific tasks, and it absolutely crushed the existing industry benchmarks.
That's incredible.
It dominated standard tests for reading comprehension, logic, and question answering. It outperformed incredibly complex, heavily engineered architectures across the board simply because its foundational understanding of context was so deep.
So what does this all mean for you listening right now? The reason your modern AI tools, your chatbots, your writing assistants, the autocomplete in your email, the reason they feel like magic instead of frustrating, broken conveyor belts of text is entirely because of the one-two punch of these leaps.
Yeah, attention and BERT.
First, attention gave the system the mechanical ability to stand in front of the giant detective's corkboard and look at all the data simultaneously, making it incredibly fast and ensuring it never forgets the beginning of your prompt. And second, BERT provided the training method, the multi-directional Mad Libs, and the trick words to build a deep, rich, resilient understanding of what those words actually mean in context.
It is a remarkable engineering triumph, but it raises an important philosophical question, and it's something I want to leave you to mull over as we wrap up.
Oh, I'm ready?
Think about how we finally solved natural language processing for computers. We didn't do it by teaching machines complex grammar rules. We didn't feed them dictionary definitions, and we didn't teach them how to diagram a sentence like a middle school English teacher.
We didn't do any of that.
No. We solved it simply by giving them the mathematical ability to measure distance between data points and then forcing them to play billions of games of fill-in-the-blank until they perfectly mapped the statistical relationships between words.
Right. We stripped all the romance out of it. It's just math and probability all the way down.
Exactly. Which begs the question, what does that say about human language? We like to think of our own communication, the poetry we write, the deep debates we have, as being rooted in some ethereal, profound meaning. But if a machine can perfectly replicate that deep meaning just by predicting missing words based on statistical context.
Are human brains doing something magical?
Right, or is human consciousness just running a highly advanced biological version of predicting the next masked word based on the context of our experiences?
That is a wild, slightly existential thought to end on. From a broken factory conveyor belt to questioning the very nature of human thought, all hidden inside 2 academic papers. Thanks for taking this deep dive with us.